We're going to start with correlation in JASP, and we're going to use neither book is great on this, and the examples in the data set, there's parts of it I found that don't exactly match the version we're using, even though it's supposed to, but we're going to roll through and use what they got. And so we'll go ahead and start with correlation. Scroll down and click on it. It says page 69, but actually takes you to page 68 for some reason. So we're going to look at the correlation, and here you should kind of understand what a correlation is. And we're going to load the jump height data set. Jump height correlation data set. You can find that inside your introduction page in Canvas. So you can see he's got it listed here, and it shows that these are the covariants. So, but he shows, depending on whether you measure it meters or centimeters, you can have the same variance, the same covariance here, the same coverage, but different items. So they're subjective scale. So it's hard to just look and tell what you have based on covariance. That's where correlation comes in, where you can come in and it's a standardized method. You could tell. So if you get closer to 1 or -1, you got a very strong relationship. As you get back down to 0, you got a very weak relationship. So you can kind of understand based on what you're looking at for any two variables, how closely related they are. Whether whether they move the same or differently or opposite. So we're going to go ahead and load that data set and just take a look. And he's wanting Pearson's, report significant, flag significant, scatter plots, and heat maps, and that's okay. Normally I don't do all of that for correlation or covariance, but we're going to start with descriptives because that's where we should start. And we're going to look for outliers, and you can click on all this, but you can get all that from within the actual calculation, and that's where you should get your Shapiro for normality. Skewness and kurtosis, you can look if you want, but as you can see, there's nothing outside of the -2 on either one of them, so you can just unclick that to save space. You can click on Shapiro Wilks if you want to. Again, they're not significant. Actually, one of them looks like it is, but when you do it inside together, the actual distribution is not. So you can click correlation matrix, and if you had a bunch of them, click in your whole matrix here, and it'll print it out. But it won't give a significance, as if it's a statistical test unless you do it underneath the regression. So that's, just another way to do it. And you can as you click on here, that's another way to do pairwise deletion and complete observations. Because pairwise and listwise, if you only got 2, are the same. Again, pairwise allows you to delete if you got a lot of variables, but a few missing items here and there, and you need the sample. You need the item. It's either you need it to be representative of the population or you need the sample for power. You can keep it into the calculations in which you're not missing anything or in which missing data doesn't affect you, and it will just purge it from the calculations that would be affected by missing data. So you'd have different sample sizes for every calculation that you run if you use pairwise. So there's times you use it, especially if you need sample size, and why they were. You can say that they were missed at random, maybe skipped over, didn't have time to look it up, but there's not a reason why they were hiding out and not responding. So we can click on here and go down to customizable and just make it colors. We want to box plots. There we go. You could do violin, jitter, whatever you want, but I'm just going to kind of run this and look. You can do scatter plots if you want. I really wouldn't, but it kind of give you that and give you density and all. It gives you a pretty smooth graph. If you only got one, there's nothing wrong with doing that. Rest of those, okay. So let's get out of that and go back to what we're supposed to be doing under correlation. Okay, waiting for initialize engine. Okay, so loaded that. Now we're going to load our two variables, jump height and leg power, into variables, and you can see it automatically populates correlation because we got Pearson's R as the default. Now you can Spearman's mainly like ordinal and Kindle's a little bit more robust, so for non-normal stuff. But most of the time we're going to be using Pearson's R, and most of the time you're using normal data, or you hope you are. So you're going to you can click display pairwise. Now that's not pairwise deletion. That's the pair correlation pairs. If you got a bunch, you can display them in one column down here, or I usually just like them as a table. You can flag significant, and it'll show you 1 is 0.05, 2 is 0.01, 3 0.001, highly significant, that, like this one is, because it's almost the same. You can click confidence intervals, effect sizes, click the sample size. You can display the covariance within that if you want to. There's really no use in doing that. These heat maps are actually useful, and that's what one of the things we're supposed to display. Especially if you have a large number. If you got a bunch of variables and you're trying to see which ones correlate together, then yeah, use a heat map. It's going to show you. Those colors are going to light up together. Scatter plot, okay. Again, it's kind of like what we printed last time, but and if you see this and you get a bunch of jumbled up stuff, it means it's not big enough for what you got displayed. You just kind of kick it out. So you can do your assumption checks here, like I said, multivariate and pairwise. If you only got two, it's going to be the same. They're not significant. So the distribution of the thing is not significant. Now, for these tables, like you said, I normally don't display all of this in there because it just makes it harder to read. I don't just report significance in here. I can look and tell if it's strong enough, and I can flag them, and that gives me little. So if I got a big table, and that allows me to look through there and see which ones are correlating together, and which ones, especially if I use scatter plot, and which ones may be two measures of the same variable, things like that. Which ones have. So you wouldn't want to put this in a straight correlation because it's too highly correlated. It violates the assumptions of a correlation. So there's different options down here. There you go. That's where you can exclude listwise and pairwise. If you only got two sets and it's all the same, it's all going to be listwise. But then again, that's where you can choose that. Usually for anything that requires pairs, you can do it. Regression, you can do it. So you could say the treatment for missing items was listwise deletion. If you just deleted every row that had a missing data, or pairwise deletion. If you're trying to keep some, you just have to list and keep up with what you did, be able to explain it. So again, I don't do effect sizes and all of that because he's got you writing up this stuff as he's saying, you can square this Pearson's R and call it R square and say it's the amount of variance explained. Well, it's the covariance. Yeah, it's the percentage of the total variance of one that's explained by the other, or it's a percentage of the total of one that's the same as the other, is what it is. It doesn't really explain it. If you're explaining the variance, then in my opinion, you should be explaining what's causing it to vary. But we don't have a causal effect here. We don't have a causal relationship. We haven't established that. We just know they moved together. And even if we did, we can use theory and common sense to say leg power is going to affect the height. Yeah. More so than the other way around. But if these were just variables, no, we wouldn't. Other than, theory that we got a priori. So I don't agree with making you write up all of this, calculating an R square for just the correlation study. And I definitely don't agree with writing up a significant result as if it was a hypothesis. So now, yeah, you can report the correlation between two, and that's the exact way you would do it. But as far as going ahead and reporting the amount of variance from one or the other, I don't. R and P is about as far as I go, unless I also put sample size in there. And normally I don't report it as typing it out. I just put it in a table, and that's good enough. Because again, you're never going to publish or sell a correlation study. you haven't proved any causation or even found big support for it. So let's go ahead and scroll down to regression, and we'll see how we can do with that. Hey, here we go. Since we keep crashing, I want to take the little video screen panel away and just use my screen, and hopefully y'all can do without looking at me for a day. So let's go down from correlation to regression. So what is it? Well, I mean, y'all should, this is again something y'all should have already covered in previous courses, but we'll go through it anyway. So you got, instead of just looking at the relationship and how each one moves together, you're actually selecting a predictor and an outcome. So you got a dependent and independent variable. Independent, of course, is your predictor. That's your cause. Your dependent, that's your outcome. That's your effect. So y, that's usually on the y-axis. So y is a function of x. Well, what's the function? Okay, well, look in here. Now this, I like this regression equation, even for simple. Usually for simple, you'll see y equals a plus bx. And I think that's what I mentioned, alluded to in the earlier video and the old video. But c, instead of saying a, let's say c, it's the constant. It's where that line that, we plotted crosses the y-axis. So, we look at the relationship between, we plot each pair, x and y, on a graph and draw the line through all those dots that finds the least amount of error. So the least squared distance between each dot and the line that goes through the middle. You find the absolute, you minimize the squared error is what you're doing. And that's why it's called least squares regression. So ordinary least squares, it's just you're trying to find the line that has the lowest squared error. So, and then you let that line run all the way through the y-axis, and there you go. That's your constant. So if x is 0, if your predictor, the value is 0, and y, that is meaningful where it crosses. Now, if you got a ratio or something that has an absolute 0 and it crosses negative, then no, it's not meaningful. I mean, if it doesn't, if it doesn't explain anything, if it can't be a negative and it turns out to be negative, then you can't use it. So you have to reset your constant at 0. But if it is, let's say you got something like advertising dollars on the x-axis and sales on the y, commonly. So wherever it crosses, say it crosses the y-axis at 10 and your constant's at 10. So you say, if I don't advertise at all, I'm going to sell 10 of these. And then from that point, we're going to follow the line up, the slope of the line. That's where your bx comes in, the slope time. So for every increase in x, that b is the rise. That's how many more dollars in sales you're going to run. And we're going to select a linear relationship at best. Now, if it curves upwards, then yeah, maybe we need to find a nonlinear, a way to express a nonlinear function as linear. But we're going to assume we got a linear relationship that could be, now it could be, further down the road you are, the further off your prediction can be. That's just natural. But in general, we're going to find the linear relationship that captures the least amount of error there. And then that gets a little more standing to say it's a causal relationship. And then what's the E for? Well, that's your error term, because regression is a prediction model. That's what it's for. We're starting out with what we know, the entire, all the knowledge for the last, weeks of data or whatever in that situation. Say we know how much we spent on sales, and we know how much, how much we spent on ads, and we know how many sales we've had. So we start out with a full set we know, and we take that dependent or outcome, and that's what you do. You regress it onto your independent. You start with the answer and you move backwards onto the questions or statements and try to figure out what's caused us to get this way. That's what a regression is. And when you start adding more variables in, you get a better picture and a better prediction, as long as those variables are significant and need to be there. So that's what it is. And your error is just establishing that, every prediction is going to be, every forecast is wrong. That's what they all have in common. Every prediction has error. So that's a simple regression. It's only got one. So you're trying to establish causation. You're using theory to set up your hypothesis, and then setting up, you know, your regression model um, to test the hypothesis that, you know, this is significant. But you got a better chance, of supporting causation with more than one variable. Um, so look at the assumptions of linear regression, and this is for mainly for multi, but the assumptions are the same whether you got one predictor or three or 10. So the assumptions of the data set, your outcome, your dependent variable you have to have a single continuous dependent variable. Generally should be normally distributed. Now your predictors can be continuous or they can be nominal. Um, Generally you have at least some continuous predictors too. That's just, and then if you have, we're going to look at the difference in these two groups. Like I said, these two schools maybe, see what variance it adds to be from one of the others. Yeah, then you can create dummy variables and, to use nominal. But in general, most of the time, you're going to have continuous predictors and a single continuous dependent outcome. You have to. Okay, outliers. No significant outliers in your initial search, and no significant outliers in the model itself. You check that by looking at the error term or the residuals to make sure you don't have any residuals over 3 standard deviations away from the mean. Um, that's the first place I look. But if I look, and if I got a bunch of significant on my box plots, and yeah, we need to look and see. If they're pretty close, I'll go ahead and run it and see. If they, maybe you're not large enough to, to bias the distribution, and maybe we'll just kind of play that one by ear. But if there's significant outliers from the get-go, when you run your initial descriptors, you need to go ahead and take care of them there. Needs to be a linear relationship between the predictor, all predictors that are left in the model, and the outcome. Also, there needs to be a linear relationship between the group of predictors, or the actual prediction, the actual equation, and the outcome. So the total prediction line needs to be a linear relationship between the predictors, all of them, and the outcome. And we'll see that in a minute. But when we start looking at our charts at the end, the graphs, independence should be independence of observations. That's where we get back to, we said we had these nominal levels. Well, let's see. You don't need to have clusters within your data that explain variance, or it could be the cause of unexplained variance. And we call that heterogeneity. So let's say we're measuring results of a statistics exam against 3 regional colleges in Oklahoma, Southeastern, Central Oklahoma, and Murray State. Okay, and we're looking at our study and GPA and all this, but we also, we failed to capture which school they're from. So we know that that's going to cause some variance. Southeastern is going to be the top. Central is going to be right on their heels, and Murray State is going to be down there because that's just the way it is. If you don't believe it, look, go ask somebody. So those groups cause clusters within. So your whole population is not monolithic. You have clusters within, and that's what we call heterogeneity, when those clusters within explain variance that your model doesn't. So there you want to create dummy variables or nominal variables to explain to show the variance explained by the different schools. And we have to show you that, at the end or later, and we'll get to modeling. So that's independence. Now, normality. Again, your residuals have to be normal, and your distribution has to be normal. And you want to check. You're checking your QQ plots, and you're checking the distribution to make sure your residuals are not correlated with your predictors. So that's your equal error variance, or your homoscedasticity. That's different from homogeneity. We also want homoscedasticity. So all along, remember that prediction line is just a slope, overall prediction equation. If it's significant, you want your error terms to be fairly evenly distributed along the outside of that. You don't want a whole bunch on one end to be way off, and then the other end to be small. Because then you probably got a missing variable bias, or you may have a nonlinear relationship that you haven't accounted for, maybe a moderator, or maybe a variable that increases um, um, gets larger as it increases exponentially. So it moderates itself basically, or two variables that cause an interaction that you haven't captured, or something. So you want homoscedasticity, all your error term to kind of be fairly similar along the line. Then multicollinearity. Like I said, your predictor, your error term can't be highly correlated with your predictors, but they can't be highly correlated with each other. You got to make sure of that. Because if you got two highly correlated predictors, then the regression model will sometimes assign all the impact to one and flip the other one to a negative. Sometimes it'll just give you wrong answers for both, or give you negative signs, or completely wrong, or it can just skew your answers uh, based on what it assumes to be the largest one. So if you got them, they're too highly correlated. One way to check, you can run a VIF, a variance inflation factor, to make sure that those values, you really don't want them over 3 or 4 because it can cause trouble, but even though they say less than 10. But you could also just play leave one out. With the hierarchical model, it's very easy to list one in a top model and then add the second one and see if it's still significant, and then go back and add the second one first, and then the first one, and see if they're still significant when they're entered, differently. So, that's another way to do it, to show that, hey, there's no difference whether we leave one or out, so it's not causing any collinearity. So, those are just different ways you can check to make sure you've met all the assumptions here of the model. So now that we've covered all of that, all right, so let's get into simple regression here. And scroll down, and you'll see we'll be using that's kind of determining how to get power, or your rule of thumb. Really, the only way to truly determine your power for a multiple regression is to download a program called, well, they may have power built into a little bit better into JASP right now. SPSS has it, of course, it's expensive. But you can always download a free tool called G-Power. Now, I don't expect you to do that, but if you ever want to get a doctorate or go on and get a master's, of science and data, then you may want to look into this free tool. Just download it, and you can. There's many different calculations you can enter, and enter your sample size, and it'll tell you whether you got 80 power or 90 power, whatever you're looking for. So we've got. We want to go ahead and start for this one. What were we going to use? I think the looking at some of squares here, looking at, he's got a line. So if this is your regression prediction line and all your plots are dotted, each one of these, the distance is your residual or your error term. So you're looking at squared errors. So again, this is your mean. It's your mean prediction along each, along the values of x. So you don't want the positive to cancel out the negative, so you square them. So you're looking for the least squared errors along the line, and that's you find the computer's going to find the line, no matter how many variables you got. It's got the least errors, but it's going to assign the variance it thinks to the strongest predictors first, and then go on, depending on how you enter it. That is. So we're looking for, when we're different goodness of fit and different terms that you're looking for. So the output for these regressions, and you'll see some terms you're looking for. R squared. And we'll talk about R, that's your Pearson correlation, but individual correlations are listed. You'll have a capital R, which is a correlation or a slope of the line. You square that just like you could square Pearson's R and assume you got the percentage of variable explained, which you do, but you haven't really explained why. Here, we're trying to explain why. So the R squared, that's the amount of variance in your dependent variable explained by your model. So you want that to be, relatively high for social sciences. Now, for things like accounting, where sometimes a 1% difference in R squared may be huge to them, because if you're looking at $1 billion budgets, then 1% is a big deal. Usually, for the rest of us, we're looking for bigger jumps. 15 to 20% at a minimum. You want to see at least about 25. So there's charts. I don't remember exactly how your book tells you to interpret it, but depending on which method we use, we got ways we want to interpret that. There's also an F model. So you're going to get an omnibus test, ANOVA, which tells you whether or not your regression model is significant. So, and we'll get into that. That's going to tell you at least one of your predictors is significantly different from zero. As long as you don't have extreme collinearity causing goofy stuff to go on in your model, then that number is significant. At least one of your predictors is significant. So you'll have that, and you'll test. That's what we say the model as a whole, the entire model, all the predictors have to have a linear relationship with the outcome collectively. So once you look at that, you can say, okay, model significant. Then you can go up and say you get a regression printout with your R squared. It's going to give you something called an adjusted R squared, which takes a little bit of variance out. It's going to give you, just multiple R, which is, like I said, the slope of that prediction line. It's capitalized. It takes into effect all of them. So for the whole sample. So you're going to look at that, and then your residuals. We're talking about the distance off of that line. That's your error term, and you're looking at the percentage explained divided by the error term, and you want that naturally be larger. So let's see what we got. We're going to load to show you for this simple regression, rugby kick regression. That's the data set we're going to load. So I've already got it. Again, it's in your introduction sheet if you hadn't already pulled it out. Once I get that, I'll just go ahead and shut this other one. Keep from using resources. And you can see we got an outcome, distance, how far we can kick the ball, based on the right leg strength, left leg strength, right leg flexibility, left flexibility, and bilateral strength. So first thing we're going to do, well, like you said, go ahead and run your descriptives and just take a little look-see to make sure. Make sure you don't have any significant outliers, nothing, just terrible. So run it for the whole data set. Just put everything in there. For every one, you're looking through here, and it's giving you a table. So let's look. We're not splitting it by anything. We don't have any nominals. Statistics. You can go ahead and click the Shapiro Wilk. I generally look. I don't think there's anything significant in there. But then go ahead and take it out, save space. You do the same thing with skew and kurtosis. I don't think there's anything outside the -2 box there. There's not. So you kind of save that space. You can keep it in there to make everything look nice and scientific if you want. But for this example, for sure, just unclick it. Now, like I said, if you wanted to click correlation covariance, you could run a correlation table sure as well right here and use pairwise or complete, whatever you want right there. And the only thing it's going to give you on both sides. Same thing for correlation, whereas you're going to get a better looking table if you just use the regression. So we were looking for what? We can just click QQ, but you're going to look for the distribution here. You don't want, this one's kind of coming a little bit off. Most of these are the last couple, which you can come off a little bit. Most of them the rest of them kind of need to be hugging the line. These flexibilities, but again, we're going to look at the distribution, not the individual ones, to make the true determination. And I'm just wasting time for the next crash, I guess. So let's go ahead and we can just kind of pull the chart or box plots, color palette, look at the outliers, and Just use the box plot. We've got one that's right on the line, but here these are 2.5, not 3. So I just go ahead and leave them in there. Nothing else is significant outlier, so just leave it. You can run scatter plots, whatever, but there's really no use. The one thing I always do, I do run a correlation table one way or the other. So whether it says to or not, I go ahead and run it because I want to see. And just me, I always put my dependents at the bottom so I can see what. I mean, I guess you put it at the top, it'd be on the first row, but I always put it at the bottom where I can see what's correlated strongly with that, just to get a look-see. Not to do anything with it, but report significance, yeah, we don't need that. We're just looking at the correlations, not. Now we're going to flag these. So you kind of look, we got some pretty high ones that could cause multicollinearity. But for the purpose of this, we're only going to use one or two of these at a time. So, okay. It's not overly correlated, but dependent. It's supposed to be somewhat correlated to have a linear relationship. But up in here, these two, flexibility and right flexibility and left strength, why is that so highly? Left strength, right strength, that's obviously left strength, right flexibility. Some of these, I don't know, this may be a made-up data set for all I know. Probably is. But you can kind of see, and it gives you an idea. So you're looking, you highlight what's. I wouldn't run anything that's up close to a 9, but for the purpose of this example, we just do that. And if you really want to show that, look, you got stuff that's pretty heavily correlated here. So you can look at assumption checks, like I said, within here, and you get an idea of normality of each individual pair. But we're not looking for those pairs. We're looking for the entire system that we're running. So, yeah, we didn't have any missing data, so we don't need that. So now we can go back to linear regression and run exactly what he told us. Now, this page in your book is not matching what's in 19.3. It didn't match what was in the last one. I don't know if they just didn't change it or why, but so they're telling us to load right strength as a predictor and distance is the outcome. So we're only going to load one. That's a simple regression, just one. So our dependent right there. Notice you got two models there. One is just showing the intercept, and then the next one. And you got 3 boxes here. I told you this is the omnibus ANOVA. First thing you do, you look here and see if your F for the system is significant. If it's not, then the models are not significant. Stop. If that's significant and you don't have anything goofy with your data, then at least one of these predictors that you enter should be significant. Up here, you're going to get your R, your multiple R, your R squared. That's the coefficient of determination, it's called. That's the percentage of variance in the dependent distance explained by the predictor. So in this case, it's the percentage of, it's the distance that we kick that's explained by right strength, I think we're told in there, and the intercept, if you keep it. So I'll show you how to separate those two in a minute. So factors, that's if you got a nominal variable or dummy variable that you're entering, but normally we're going to use covariates for scale variables. So now we look at our model. This is where we get our model. So model 0, that's our control or just our intercept to see if that's significant on its own. But then what does it do? It drops down when you put a predictor. That's where that omitted variable bias, right? So this is just your average Y. And then when you put your predictors and models in, it should not be significant. Or it should not be as large. It can still be significant. This one just actually isn't. So now it is meaningful, 57 feet, but it's not significant. So what are we looking for? Estimates, model fit, and Durbin-Watson. Now, this is not a good case to use Durbin-Watson. Durbin-Watson is autocorrelation. Usually you'll get that with time series. So accountants use that one a lot. See if I can kick this out without, okay. So Here's our models. And if you got control models, you can enter multiple models. You can do, a intercept and then intercept with control variables, and then go down to a third with the prediction that we're looking for. That's how you do hierarchical multiple. So we want Durbin Watson. Notice that ours is different. His is listed under residuals, which it shouldn't be. Well, I guess it's testing. Yeah, it is. That's your model summary. It shouldn't be under model summary. Well, they put it where they want, I guess. Um, we wanted case-wise. Now, these case-wise diagnostics, you use Cook's. I usually just use standard residual. It's going to list any item that's where the residual or the error term is more than 3 standard deviations away from its mean. So that's a significant outlier for the system. Estimates, it's automatic. So estimates automatic click. Now, if you wanted to bootstrap it, which I don't know how to do, we're not even going to do that. If you wanted confidence intervals for all these betas, that's how you do it. Just click right there. 95% confidence interval for your unstandardized beta score. If it crosses 0, then it's not significant. If it can be 0, if its beta could be 0, we're testing whether it's significantly different from 0. It can be negative if it decreases, has a negative impact. It can be, obviously positive if it increases the overall mean. You can click descriptives and kind of see the mean, standard error, all these. We don't have any instances. You can change that to a 2 and look for anything that's more than 2. Case number 3, but it's barely over 2. So even if you did that, you probably wouldn't delete that. You can use 2.5. Usually you either use 2 or 3, and 2 is extremely stringent. Normally looking for 3. This is the type, how the distance, how it's measured. You don't have to worry about that. You can look at the statistics of your residuals, see how they're standard area prediction, all of that. You don't have to. He didn't ask you to. If you click this, append residuals to data, then you're creating new columns with your prediction error for each. So it's going to be the predicted. If you plug in the values of X for your prediction, plug in values of your X into your model, multiply your beta times the value of X, add your intercept, that's your prediction. Then how far off it is, that's your error. So you can append those residuals, the error, and make new columns for that. And then I'll go ahead and look down here. He didn't show you to, but this Durbin Watson, let's look at that really quick. Durbin Watson measures autocorrelation. So for time series, especially where, what it measures is the likelihood that a variable is predicting itself over time, basically, just to sorting it down. So like I said, you only see it with time series where you got overlap here, especially, so you check for it, and it ranges from 0 to 4. So as long as you're kind of within, you're not for your, closer to 2, the better, but as long as it's between 1 and 3, usually it's okay. And the intercept, I don't worry about the intercept predicting itself. So you're looking there to see, making sure you don't have that kind of bias in there. Like I said, you got your model significant at 0.002, F extremely significant F value, large F value. So that means at least one of these is significant on model 1. Not worried about model 2. We're just worried about the significance of model. So or we're not worried about model zero. We're just worried about the significance of our predicted model. So we do. Our predictor is highly significant, 0.002. And looking at our, you can look at our confidence interval there if you want. What else we got we can use? Um, Tolerance and VIF is something you can kind of click on to see if you have, but not with just this. If you got multiple variables in there, you can look to see for collinearity. For your multiple hierarchical models, R squared change and F squared, you can see how, or F change, see how much is added with each step. Um, no outliers there. You didn't have to produce residual statistics. I just did. None of this other we're not going to get into, especially not with singles. So your plots, did he tell you to plot anything? So we're looking, at the results. The way you explain that, explain 61, and your adjusted R square, with every extra variable you add, it reduces it just a little bit. It reduces, so you got the explained variance divided by the error, or the explained variance over the total variance is a percentage of the total variance is your R squared. You multiply that by, what is it? Multiply that ratio times, what is it, n minus 1 over n minus k minus 1, where k is the number of predictors. If you include so it's your number of independent variables plus your intercept if you include it in the model. So it's reducing by just a little bit every time, and that's to count for the error term. Root mean squared error, that's just a way to compare error over different models. So you pick the model with the lowest adjusted R square usually, and then it should have the lowest root mean square error, but you explain it in terms of the R square usually. So is this one model significant? F17.533 P.002, and explain 61.4% of the variance in distance. Hypothesis 1, significant, with our strength positively related to distance, T of 4.187, with a beta of 6.425, T 784 P, or not T 0.4187 P 0.02. You kind of write that up, or you could show the confidence intervals, whatever. Residual statistics, and what else? Because I have to jump up. See what else he told us to show. Residuals versus predicted in your QQ plot. I usually do a little bit more than that, but that's okay. So you can see where we say these need to be kind of fairly the same all the way across. You don't want to see any, your residual, the error needs to be not all one-sided, or little down here and big up here. Your standardized residuals need to be fairly close to this line, not so you determine that. And I usually just go ahead and print a histogram to see if they're, fairly. And also residuals versus covariates. So you don't want any of your predictors highly correlated with your error term. That's a definition of endogeneity that y'all supposed. Now, what causes it? Well, y'all are supposed to find that out, but that's the very definition. So basically, the model's kind of predicting itself through a mathematical anomaly that way, but it's not a true statistical result. So yeah, you don't. So the residual should be fairly normally distributed, but the error term should be even across, the whole prediction line, and it shouldn't be correlated with any of your predictors. So, those are tests, for, and your goodness of fit, well, that's, you're making sure your error, but your goodness of fit is the amount of variance explained. So your goodness of fit statistics, your F, your model significant, and your R squared usually is what we use. So that is simple regression and its plots. So we will come back to this next time and add some more and show you multiple regression. All right, so one thing I forgot to tell you, or I actually told you, but I didn't show you exactly where it's written in the book there. I just kind of read out the way I would have done it. But he's got everything you're going to want to pull out when you go to write these things up. He's got it written in there. So showed you what the model summary is, your R squared, percentage of variance explained independent by the model. That's both the intercept and the predictor. Anything you left in there. Told you about so and adjusted. But when you go to pull it out, you may want to highlight it, just kind of keep it there. R squared value of 0.614 tells us the right leg strength accounts for 61.4% of the variance in kick distance. Okay, that's a good simple way to put it. So, it's not going to let me highlight the 6.14. So, but I mean, you can look and see. And then you come down your omnibus and over. This tells us, basically if our model's good. So the F statistic is significant. P equals 2. Tells us the model is significantly better predictor of kicking distance than the mean distance. So it's the model outperforms just the mean. It has predictive value. And now you report it as, here's the way you report your F statistic. The model significant, F111, that's your degrees of freedom. 1 comes from the fact you got one predictor. Your residuals, N minus K minus 1. So K is 1. That you, there you got 2 predictors. So K minus 1. So N minus K minus 1. You started out with a sample size of 13, so your total degrees of freedom is going to be 12, N minus 1. You got N minus K minus 1. With one predictor, you end up with 13 minus 1, that's 11. That's second degrees. That's degrees of freedom for your residual. 17, and then your p-value. So that's where those numbers come from. Also, I told you that you can plug it in, but here's exactly. So if you're looking for a leg strength of 60 kilograms, you can plug it into this model. So it's going to be 6.425 times 60, because that's your x value. So remember, b times x plus 57c, and that's going to give you your distance, and you can predict what your distance should be with a leg strength of 60 kilograms. So, that's a simple way, example of how you do that. Kind of look through there. And if you come down here, like I said, I read through this. He's got it written up exactly as the way you want to write it. Simple linear regression used to predict rugby kicking distance from right leg strength. Excuse me. Leg strength was shown to explain a significant amount of variance in the kicking distance. F degrees of freedom 1, 11 equals 17.53, P of 0.002, R squared equals 0.614. Regression coefficient B equals 6.452 allows the kicking distance to be predicted using the following regression equation. And you can write out the equation normally, but normally this is where I'd come through here and say H1 is significant, B 6.452, comma T, whatever it was, 4 point whatever, the P value, whatever it was, and close it. But that's up to you. That's also a way you could do it if you didn't specifically state a null hypothesis. Well, normally we don't state a null for unless you count it. We don't state a null for regression. We just state H1, H2. Depends on what your field is and what's common. That's why you look up stuff in your field when you're looking up peer-reviewed journals. Find out what's used, what the lingo is, what the conversation streams are, whether they're quantitative or not. So now we will move forward after I got that to multiple regressions. All right, so we seem to be doing a little bit better without the little video of me in the corner. So I'll try it. Hopefully, y'all can understand me and follow along. So let's come back to page 80, and we're going to be looking at multiple regression this time around using the same data set and same thing. So you can just close these up and use it, or you can close it out and start over. It doesn't matter to me because we're just practicing here. Um, so back to the book. We're going to start off at, I got this blown up a little bit, so I'll see page 80, multiple regression. So look at his definition and how he got his regression equation listed. At the top, we got the outline for simple regression, just like we just did. Y, your outcome, equals your constant or your y-intercept plus the slope times x plus an error term. So if you only got one, you got to, wherever it crosses the line, that's where we start, and every increase in x yields b increase in y. So come down here and let's look at multiple regression. Well, you're doing the same thing. You just have a lot more predictors or influencers. So these independent variables, x1, x2, x3, all the way up to as far as you need to go, but we're just going to stop here and let's assume we got 3 and this is the error term. You still got a constant. Maybe that's a floor value. And let's say this x1, how are we going to use this? And let's say this x1 is square footage. X2, say it is bedrooms, number of bedrooms. X3, number of bathrooms. So this is, a partial slope relative to this. This is the slope of this variable. This is the slope of this, and it's all kind of going to even out depending on the weight of each one to one straight prediction line. Now, how different these are, may cause some of your points to be radically off the line. You may have a higher residual, or you may not. So what are we doing? What we're doing here? So you got a baseline price. Let's say for every bathroom we add, B is how much is it going to increase our price? For every bedroom we add, how much is it going to increase our price? For every square foot extra we have, how much is it going to increase our selling price? That's what we're doing. Like I said, it's regression. You're starting with all the answers and moving backwards to find the statements of the answers or the questions. So, and where's that whole slope here going to? So, how do you kind of interpret these? If these are negative, that's going to be something, if it's significant, that decreases the overall outcome. That doesn't mean this is negative or these are negative. It just means it's below the mean, below that overall prediction line. So it's going to pull the average down. If it's positive, it's going to push the average up. So you can kind of think of these, and you got 3D 3D displays can kind of show each one of these as tent poles. So the ones below the mean are lower, so they pull your surface area down. The ones above it, push it up higher. So now you're covering for that overall slope. If you can draw one straight line, through it, that's your prediction. So think of it that way if you need to. I think actually maybe the other book actually did diagram it that way. So to show you, so there's different. So how do you, if you're looking at these different ways to enter this into your model using JASP, so or using SPSS or whatever, there's different entries. So to determine these values, these beta scores for each, so you're looking, your average y should equal the y-intercept plus the average value of x times this beta and average value of this x times this beta. And so you're trying to figure out what all these values are for each x to determine as it rises and falls, what it needs to be to keep a good prediction line. So the size of these are going to be determined by how the computer interprets the impact is. So the higher beta is going to have a higher impact on the outcome. So it's going to be more, the partial correlation or the individual correlation between should be higher for those, and it should be more significant. Um, Sometimes if these, that's what I was saying, if you got two variables that are very closely or highly correlated, it can mess up the math, and you can assign all the variance to the wrong one and none to the other one. You can have signs flip where it looks like it's decreasing the value, but it's really not. If you ever, so, or sometimes it can just be correlated but not related in a causal manner. So the correlation will make it look like it should predict, but once you find the real root cause, this, it becomes not significant. So how you enter these, which one gets entered first, can depend on how much variance is shared to it, because everything else is missing data, missing variable, or omitted variable at that time, and then it gets added later. Whereas if it got added first, it may get the lion's share. So entering the enter is the default method. Exactly how you put it in there is how it's going to show up in your model, and it's how the computer's going to run it. It's going to enter it into the model, as long as it hits the parameters of significance that you put in there. Backwards, it's going to put all in there, and they're going to be entered backwards in decreasing order of significance. So you enter your least significant ones first, if I'm not mistaken. Um, it puts all these in, it pulls these out, the ones that are less significant backwards, it pulls them out. Forward will enter them into it in order and up until the point they're not significant. So, and then stepwise is the granddaddy of all p hacking. That's where you just enter it in there, and it's going to enter it in the same as forward, but every time it's going to recalculate to see if anything needs taken out, and it's going to keep putting stuff in. So it's going to end up with a model that just picks everything that's significant and basically calls everything that don't. So you go in with no hypothesis, put a bunch of data in and see what's, well, it's kind of dangerous. Sometimes you can get, it can be just a mathematical anomaly. It can be correlated with an error term, or, homogeneity, or, you can have something called suppressor effect where can drive researchers nuts. Even when you're doing things right, you've got, all this error term that's suppressing the correlation, or something is suppressing the error term, making it appear significant when it's not usually. So maybe you got 2 or 3 variables in there together, highly correlated, and they're kind of covering up the error term, so allowing something else to be significant when it's really not. So you have to be careful. Kind of look at, that's why I always run correlation tables. Just give me an idea of what I should be looking for that might be wrong, or kind of looking at everything in here kind of looks too perfect. So maybe I want to see cross validation, or kind of giving away. Well, actually, it's week 5, and I'm giving away in it. So give me an external sample or a split sample and compare. Make sure you're good with one and the other to make sure everything's okay. So get into that with multivariate statistics a lot, where you got multiple indicators for each variable or construct, and then that predicts another predicted construct. So your model's big and long. Here we just got manifest items predicting another manifest items. It's multiple regression, yes, it's got multiple factors, but not really the same as latent constructs. So, but those are the way they're entered and how they are. You have to report that, and you kind of step back, and especially if you see stepwise. Why did you use stepwise? Didn't you predict something? Didn't you already have hypothesis set up, or you just seeing what's you just throwing everything on the wall to see what sticks? That's p hacking. That's unethical. It's wrong. So just kind of see. So here, it's going to take you through all these different ways to enter them and see what regression it gives you, and then show you. And on this one, unlike the simple regression, um, the interface, the pictures exactly what you have, if I'm not mistaken. So I'm going to close these up, and then we're going to go into regression and linear regression. Okay, now let's enter distance as our dependent. That's our outcome, our predicted, and then our predictors are going into the covariates, and we're going to enter, I think, all of them, right? 1, 2, 3, 4, yeah, all of them. Exactly the same way they're listed. So strength, flexibility, and by, yeah, like that. So then I think we're going to use enter, right? Use enter and take the following options. So we want Durbin Watson, we want our estimates, residual statistics, like I showed you a while ago, even though they didn't, your case wise. So anything more than 3 standard deviation, any error term more than 3 standard deviations out, not the actual variable, but the error term for that line. The model fit, I think. So we'll just see what we got. See how much. So here's your model and how you do your stuff. So model 0, that's going to be your intercept. Then you'll come down and it will add. See, it will add your covariates or your independent variables to that in step 2. So like I said, if you were controlling for strength to determine flexibility, you could enter these 3 in the top, or in like a model 1, or you could enter it in model 0. Enter it into model 1, and in a model 2, you could enter flexibility, and you can see how much flexibility those two add to the model above strength, if you so desired. But right now, we're just going to kind of stick to what they're doing and come down, see what statistics we want. We want Durbin Watson, our estimates. Model fit, there it is. Statistics and case wise. Maybe we only had 3 last time, or did he only have 3? Maybe it's different for simple than seeing. No, he only had 3 and we had 4. So yeah, that's just an old. Even though they updated the book, they left that one out. Missed that update. So our statistics and then our case wise at 3 standard deviations away from the mean, we're not going to apply those. But if you did click that, it would add it to your data set, and then you could go back in here, and as you export your CSV or export the data, it will capture it and enter it. So and add the new columns. So Anything else? No, we're just going to see what we have. So Durbin Watson, again, not a problem. I don't think. Here, yeah, I got the same thing. So our R square 0.814. Notice on up there, because the more you add, by definition, your R square is going to go up. It's going to increase the variance shared because all of them have some shared variance. Your adjusted is going to come down the more you add. So what you don't want these to be dramatically, so because that means you got some that just aren't adding value there. So it's R squared, so 81.4% of the variance in the outcome, but we don't really know how much of that is error because we're showing. So, and that's where you go through and the ones that aren't significant, really you pull those out and report them as not significant. You report exactly what you got, and then you pull them all out and run a final model without them and say, this is my parsimonious model. So parsimony, uh, smaller and simpler. So directing to the point. So prediction model. So it doesn't include the factors that are not significant usually. Now in schoolwork, a lot of times we do. I don't know why. Or if it's a pure predictive model, sometimes you put it in there if the prediction is good. But if you're testing theory, you pull them out. So here's our p-values. They aren't very good. Actually, with everything in there, we're not showing a whole lot significant over. Wow. Our we got that significant. What the hell is this? We got problems somewhere. We got too much. We got things fighting each other. I would imagine either that or sometimes an outlier do it. We're not showing any. Um, Residual statistics. So how is that? Some of it's significant. We just showed it. So this is kind of what just throwing stuff in there can do. It can cover up significant. That suppressor effect I was talking about. It's hard to find, or leaving things out can create significance because pulling variance in it should go to another variable that's just not in the model. So you got to be careful in what you do. So here's model one. That's just your intercept, and it's going to show it highly significant. And then when you enter all your factors, it's nothing significant. So I don't know why this p-value is significant. More likely you got collinearity or something. So maybe extreme collinearity. I believe when I pulled that, we had a lot of it. So I can click on VIF and just see really quickly. 6 and 7s, yeah, that's going to be on up there. Probably causing you fits. They say anything below 10, but really anything above 3 or 4 can give you problems. Anything that high, yeah, especially if you got multiple that high, no good. But, that's kind of how you enter them, how you interpret, the intercept you're just looking, but you could, to be honest, you don't have most, just enter that into SPSS, you don't have to enter it in as a hierarchical, it's just going to put it all in the first box. And if you enter multi-step, then you can enter what you want. Thing is, just don't get multi-step or hierarchical confused with stepwise. They're two different things. Stepwise is just it's p-hacking, throwing everything out there to give you supposed to be a parsimonious model, but the way it does it. So if you're determined to see if you got collinear problems, like I told you before, you could leave one out, or you could use the forwards and backwards to determine if one's causing endogeneity or multicollinearity or something. And if you get difference, then yeah, you do. So what's the next step we were going to do? We were going to rerun the analysis, but now choose backwards, right? Yeah, I think so, and see what we get. If we get the same thing as here, and we got one that's, but it didn't enter all of them. It only entered some, right? So, okay, let's shut this one up and try again. Regression, linear, distance, all of these. So backward. Remember, that's not the order they're listed. That's based on its significance of the model. And then we're gonna what we want to. I don't know if we want R squared change. I'll click it. Is it supposed to? No, but we will. Durbin Watson. These. Uh, this is kind of what it's using to tell when to enter something into the model or when to pull it out. So let's see what we have. We have the same thing he does. So it looks like it. 1, 2, 3, 4. Okay, and I did an R squared change. I don't think they asked for it, but that's how you read that. So with every subsequent model, that's the additional value it's adding to the model. So nothing's adding anything based, your R squared is actually coming down. Oh, because it's backward. It's pulling things out. That's why. Okay, right. That's why you wouldn't do a. That's why that doesn't really help you with that one. It's forward where it's putting it in, right? Okay, so you start off and you can see the model and it's putting it in, and as it's pulling it out, it's pulling things out to see what's left, significant. And these other p values are capturing more than the variance that they, I guess, should have been catching. So we got one that's moderate, and then you get down. We got two significant right strength and bilateral strength that are all that's left. Those two. So they may be the only two significant factors you have. I don't know. So now we're going to do the same thing. That one's forward. Backwards, we do forward. All right. So that's not good. There. Covariance. So now we're going to enter them forward. So it's going to be adding things up to the point. So you may not have 4 models this way, and you don't. You don't have them backwards. So it's doing the modeling, so you don't need to do that. So you can click whatever we're supposed to be looking for. Durbin Watson. Any of those been significant at all? I don't think so. Not even close. Nope. Not really. Nothing. So Durbin Watson, but if we went and looked at that VIF, that might be your variance inflation factor. It kind of determines whether you got one or more variables, usually collinearity, causing to artificially inflate your variance or your R squared. Still no outliers, but forward, what we got here, we're only coming up and entering one. It's highly significant. That's for only one model forward. But but we showed 2 significant a while ago. So what does that mean? The best model may be predicted just off of that. It's only going to enter it if it's increasing the value of the model. All right, so then, is that what we end up? So, which one? Okay. Backwards, and that's how you report that. Just for those 2 variables. Residuals, predicted values. Look, that's no pattern. That's good. Of course, that T is not ours, not mine. So, all right. So that's how you write the results of those 2 using what? Backwards. Forward, you would just show. That's logistic. So out of all of those, it's showing the backwards gives a better model. So I thought we were supposed to choose that one. Maybe we were supposed to choose forward first and then behind. So enter first, then all right. So that was enter. All right. The next one we did was backwards. All right. That got us down to these 2. And that R square was what? I don't know. 78.2. Then all right, so yeah, it looks like we just did, backwards and enter. I could have sworn in the old book we did all of them just to see. Maybe not. Maybe they didn't do forward and stepwise because it's kind of p hacking, like I said. So I can show y'all that's forward. So forward, just gonna keep pushing in anything it gives, pushing the next most significant thing as long as it's above a certain threshold, basically. So right strength by level strength. Why it didn't? That's showing flexibility on its own as a higher predictor. So, and it may not be. Once it pushed that in, then the next one didn't meet the thing. So didn't meet the threshold. What was so these 2? Yeah, F square 78.2, and for just that one, the R square was only 64.9, and then it didn't let anything else in. So you see, it can give it and take it away. Let's see what stepwise does, just to see. But again, this is, you need to have a good reason for doing this. Not, I don't feel like going through, do the lid review. Stepwise, and it only gave. Look, it only gave because that's the most high, so it's leaving out. That's fine. Sometimes it won't give you. check them all, but you don't just use it to find significance. So because sometimes obviously one factor can be more significant, but your whole model it hurt you. So if you enter VIF on all these, which I would have, with only one, it's not going to be correlated itself. Um, Back up here, let's click on VIF. Again, tolerance. So if one's, that's only one, so it's not going to show anything. The VIF is five, tolerance is 90, then VIF is 10. That's how that. So yeah, up here you got some collinearity was probably causing problems, and then once you get some of them out, you start seeing different significance levels. That's just a little bit higher, and then you get them down here. But actually, it's just weeding out things that aren't significant, so others can pick up. Yeah, it's kind of a mess of a data set. So basically, so that's how you do that. So how you would enter? Let's say we're going to control. Like I said, we're going to control for strength and see what flexibility adds. Let's regression, linear, center of dependent, distance. Maybe let's see. We're going to control for enter total linear flexibility and bilateral strength. We're going to control for strength and test flexibility. So how you do that in your model, you could add a model or you could just flip it up there to 0. You know, you have one control model with the intercept. But so you could pull, you got both of these, you just pull one of these out. We're going to control for strength to test flexibility, right? And there it is. They won't let you move any more at the bottom. So now what you have, should have 3 models. You got the intercept. Okay, so it didn't give me an F for just the intercept. So it's looking for, we got bilateral strength, which is highly significant. And I've ended up with strength twice. Flexibility there. There we go. Had to put it in the bottom. There we go. So you end up with actually strength isn't 100% significant. There is a 0.055. Best I can tell, kind of becomes not significant once you add other things. That can happen. What about R square? See what it does when it comes to our statistics. That's where you use your F change and your R square change. We can look at these case wise. That's good for that. Then we'll look at some of these graphs to kind of determine. So from here to here, you're looking at R square change, obviously from nothing to 1, and you gain 63%. But the difference, so it adds an extra 12.5% variance explained to the model. Above and beyond strength. So that's how you read and interpret that if you're doing a hierarchical, a multi-step hierarchical multiple regression. None of our Durbin Watson look bad, so I ain't worried about that. The VIFs here, not bad. That looks bad. Our model specification, no, our plots. We can look at our plots. So our Residuals versus covariates. You want to make sure you don't none of your error terms are correlated with your predictors. That's probably what I should have graphed. Uh, no, just kind of a hodgepodge mess. Residuals versus predicted. How does that look? Nothing really. Histogram. Are they fairly? I mean, no, they're kind of inverse from normal, aren't they? But they're not skewed or anything. QQ. Yeah, that's fair. That's what you want to see. So nothing looks really that bad, in that model. Okay, so if I hadn't put you to sleep just yet, let's take a minute just to look at, I don't know, let's see if we can look at the maybe the correlation between LDL cholesterol and hours spent watching TV. So bad cholesterol levels and sedentary lifestyle. Okay, we were going to look at a correlation. So now if we were going to look at that, we probably want to flag significant. I don't report significant. That's just me. You can, if you want to. Me, that just looked better. I think maybe we wanted scatter plots, statistics. I don't know if we want a heat map, but we could throw it in there. Sure as the world. Those scatter plots and statistics kind of gives you an idea. Well, not much one did it. We wanted to look at assumption checks. So we're right at 1.050. I'm hoping that's actually more because that looks like we're right on, test for normality there, ain't we? Let's say densities. Maybe I did because that'll give you that, and then you can see it's fairly normal. Um, so now, if you were looking at all that, you could see, 380, good correlation. There it is. Then we were going to turn this into, what if we were going to turn it into a regression model? All right. Dependent, bad cholesterol levels, and predictor, hours spent watching TV, sedentary lifestyle, maybe. If it's believable enough, somebody will believe it, right? So, what we're going to look with this. So, we don't need the model. Maybe some of these statistics we're going to look at. If I click tolerance, we don't need R-squared chains. Statistics case-wise, just to make sure, no outliers. Okay, look at our model here. We can plot it. If we just wanted to. Oh, okay, that's look dandy there, doesn't it? VIF's not going to show up because it's only 2, right? So, there, that's your residuals. They're standardized. That looks good. That. It looks like the residuals are perfectly correlated, but this is supposed to be kind of, all right, so off of this, we're going to look at how much LDL increase if no hours of TV. You're kind of looking at the intercept. For the second model there. Just saying. F value for your main model. R squared. Let's see, the R is the same as correlation was, but if we would be asked for every hour increase, what's the increase in LDL? A lot of people in the past had put 380 and missed it because no, that's the correlation. It's not the predictive slope. The slope is in the regression model, so you have to control for your intercept. then it starts and it's slightly lower. If you know where you're looking, you'll be able to get that one. So maybe, maybe we can look at correlation between or correlation for a VO2 max study with age, weight, heart rate, gender, heat map, and see a little regression model. Remember if we were asked to look at the assumptions, we can. That one's highly significant though, isn't it? Hmm. Maybe why you weren't asked. It's for multi, right? Pairwise. Yep. Age is driving it there because it's part of the calculation to you. Okay. All right. Not a problem. Now, if we're going to create a regression model in which we were going to test weight and heart rate, controlling for age and gender, then you enter everything in there. So VO2 max, that's just if you were so inclined to do so. Um, VO2 max, you're dependent, so your three scale variables go in covariance and gender is factor. Okay, well, you could either leave model zero alone and then come down and enter as an intercept and then put uh, your two control variables in model one and your predictors that you're testing in model two. That's one way to do it, but it's going to do away with model zero anyway because it's going to tell you it can't tell you anything else because you don't have any predictors. So why not just throw them in there with the intercept? Um, just use them as controls anyway. So I throw those into model zero, age and gender. And then click, R squared change, adjusted R squared, kind of gives me an idea where I can see. And then you can kind of look, just give them a look, see any p-value. Model zero, your F, highly significant there. So the model's good. So F 470 equals 17,426, P less than 001. So a couple of questions I think were considering all factors, how much does being male add to VO2? And a lot of people were looking on your first model, your control model, but that doesn't consider all factors. Once you throw everything that you were testing into the model, there's only one model that has everything in it. Then you look at male and pick. So I had a couple questions that said, how much does weight decrease it? Maybe how much does heart rate decrease it? Or maybe how much does age decrease it? I can't remember. But they're negative, and I ask you how much it decreases it, which is kind of an asinine way to ask you a question. So those are set to accept because it decreases it by a positive number. I was wanting to put a negative one. So if you put positive, it'll accept it as long as you put the right number. If you put negative, it'll accept it as long as you put the right number. So all you really got to do, your overall R squared, I think I went ahead and accepted either or for estimated. It's supposed to be your R squared, but I think I accepted it, adjusted simply because of the way I asked the question, or I can't remember. But it's kind of how you did that. Y'all hadn't figured out that I just did your homework. So for those y'all are still around, have a good week, and I will try to get up the little term project that I was going to do. Apparently, the camera's what crashes it. I'm just too ugly for this thing, I guess. So I'll either have to switch back to OBS. Problem with that is I'll have to reset up my whole green screen and out area instead of just using the blurred on the laptop, which is way quicker when it works. But when it's not, it takes, it adds days to every project. So Sorry for the delay, but here's a little bonus for those of you that watched it and tried to learn something, because if you went through all of those examples and still sticking around, and you stuck around a little more, you ought to be well happy with chapter 6. So again, sometime later this week, I'll try to get up, a little term project where I can show you how to pull data from an actual data set up a regression model, and use it, and then set and interpret hypothesis and write them up. So you'll watch that and then answer some more questions about it, and you'll go into all your other videos. So obviously, this one's not required. It's just a bonus for people that want to learn about regression and need some help. So there you go. And be sure to send me a message or question answer board if you need anything else.